A galaxy is being torn apart before our eyes. What if our own Milky Way is being eaten alive at this very moment? This is not science fiction. It is the reality of galactic cannibalism, a process where the largest galaxies in the universe consume their smaller neighbors. It is the ultimate cosmic food chain, and by the end of this journey, you will understand how this violent mystery shaped the stars above you and the atoms within you. We will uncover how astronomers find the evidence of these ancient feasts and ask if a similar fate is already written in the stars for our galactic home. What does it feel like to live inside a gentle giant that might secretly be a predator? The heart of this mystery lies in a simple term: cosmic cannibal. This is not a monster from a dark corner of space, but a galaxy, often a massive elliptical or a grand spiral like our own Milky Way, that grows by consuming its neighbors. It is a process of galactic evolution, driven by the most fundamental force in the universe, gravity. Picture our solar system, where the sun's immense gravity holds all the planets in their orbits. Now scale that up to an unimaginable degree. A large galaxy possesses a gravitational pull so powerful it can capture entire smaller galaxies that wander too close, drawing them into a long, inescapable dance. This gravitational web is woven even tighter by the presence of dark matter, the invisible, mysterious substance that forms a vast halo around galaxies, adding immense weight and pull to the entire system. Think of it like a spider's web, where the visible galaxy is the central spider and the dark matter is the nearly invisible, yet incredibly strong, strands that trap anything that flies into it. The cannibal galaxy does not quickly devour its meal. This is a feast that unfolds over billions of years. The smaller galaxy is first stretched and torn apart by tidal forces, its stars and gas slowly siphoned away and blended into the larger galaxy's body. This relentless process does not just make big galaxies bigger, it fundamentally sculpts the architecture of the cosmos, building the giant structures we see in the deepest telescope images. It is how the universe builds its titans, but this raises a deeply personal question: is our own galaxy, the beautiful spiraling Milky Way we call home, one of these cosmic predators? The answer, uncovered by astronomers in recent decades, is a definitive yes. Our gentle giant has a violent past. Look up on a clear, dark night and you are gazing at a cannibal. The evidence is written in the stars themselves, in the form of ghostly rivers of light called stellar streams. These are the shredded remains of smaller galaxies that ventured too close to the Milky Way's immense gravity. One of the most famous is the Sagittarius dwarf spheroidal galaxy. Once a proud, independent island of stars, it is now being slowly torn apart. Our galaxy's tidal forces have stretched it into a long, luminous ribbon that wraps around the Milky Way not once, but several times, like a cosmic serpent consuming its own tail. Its stars are being siphoned away, joining the billions already in our galactic halo. This is not an ancient relic, it is an ongoing feast happening right above our heads. This understanding was revolutionized by a remarkable spacecraft named Gaia. Launched by the European Space Agency, Gaia is not taking pretty pictures of nebulae. Its mission is to precisely map the positions, distances, and motions of over 1 billion stars in our galaxy. Think of it as creating the most detailed three-dimensional map and velocity chart of the Milky Way ever made. By tracking how stars move, Gaia has allowed astronomers to rewind the cosmic clock. They can trace the paths of stars in these stellar streams backward in time, identifying their original galactic families. Through this, we have discovered that the Milky Way has consumed perhaps a dozen smaller galaxies over its lifetime, growing fat on these ancient mergers. Our galaxy's majestic spiral disk and its vast, diffuse halo are a patchwork of cosmic conquests, and the story does not end there. The future holds an even more colossal act of galactic cannibalism. Billions of years from now, the Milky Way will meet its match. Our nearest large galactic neighbor, the Andromeda galaxy, is on a collision course with us. Currently about 2.5 million light-years away, it is hurtling toward the Milky Way at an incredible speed. When they meet, it will not be a simple crash and destruction. Instead, the two galaxies will perform a slow gravitational dance over billions of years, their structures distorting and tearing as they pull each other apart. Eventually, they will merge completely, their stars mixing to form a new giant elliptical galaxy, often nicknamed Milky. In this ultimate act, both galaxies will cannibalize each other, ending their separate existences to create something entirely new. So the cosmic food chain does not spare even the largest predators. It simply places them on a longer timeline, where today's cannibal becomes tomorrow's meal. But for now, the cosmic predator approaching us is the Andromeda galaxy. It is the largest galaxy in our local neighborhood, a breathtaking spiral of 1 trillion stars visible to the naked eye as a faint, fuzzy smudge in the autumn sky. For centuries, it was simply a celestial curiosity, but we now know it is a monument to galactic violence. The Hubble Space Telescope has peered into Andromeda's depths and uncovered a shocking truth. Surrounding its majestic spiral arms is an enormous diffuse sphere of stars called the stellar halo. This halo is not a natural part of the galaxy's birth, it is a graveyard. The stars within it move in chaotic, random orbits, a clear sign they are not native to Andromeda. They are the survivors, the refugees from dozens of smaller galaxies that Andromeda has torn apart and consumed over the eons. The evidence suggests Andromeda is a far more voracious cannibal than our own Milky Way. While our galaxy has feasted on a handful of dwarf galaxies, Andromeda's halo contains the remnants of galaxies as massive as our own, entire cosmic islands devoured in colossal mergers. Its history is written in this ghostly stellar fog, a chronicle of conquest on an epic scale. This means the galaxy speeding toward us is not just a beautiful neighbor, it is the most successful predator we have ever observed, a titan built from the ruins of others. This galactic feast unfolds with a terrifying, beautiful precision governed by gravity's unbreakable rules. The process begins with a close encounter, a cosmic near-miss. A smaller galaxy, perhaps a dwarf spheroidal, drifts too close to the immense gravitational well of a giant like the Milky Way. It is captured, unable to escape. This is not an instant collision, but the start of a multi-billion-year dance of destruction. The first visible sign of the meal is tidal stripping. You can see this effect on a smaller scale with our own moon's gravity pulling on Earth's oceans to create tides. Now imagine that force scaled up to galactic proportions. The side of the small galaxy closer to the cannibal feels a stronger gravitational pull than the far side. This difference, the tidal force, stretches the victim. Long streamers of stars and gas are pulled away, forming those luminous rivers we see as stellar streams. The victim galaxy is literally being pulled apart from the outside in. As the dance continues, a second force called dynamical friction comes into play. Think of the small galaxy moving through the vast halo of dark matter and faint stars surrounding the larger one. This is not empty space, it is a diffuse medium. The motion of the victim galaxy through this medium creates a gravitational wake behind it, like a boat moving through water. This wake acts as a drag, slowing the smaller galaxy down, robbing it of energy and momentum. This causes its orbit to decay, drawing it inexorably inward toward the cannibal's core. The combination of tidal stripping and dynamical friction is a 1-2 punch that systematically dismantles the victim. Now what happens in the chaotic core of this merger? Here, the supermassive black holes play a pivotal role. Most large galaxies, including our own, host one of these monsters at their center. During a major merger, as the gas and stars of the two galaxies intertwine, the two black holes begin a gravitational dance of their own. They sink toward the center of the new combined galaxy, eventually orbiting each other. This process pumps tremendous energy into the surrounding gas, sometimes triggering spectacular bursts of new star formation or fueling brilliant quasars. Ultimately, the black holes may themselves merge in a cataclysmic event that sends ripples through space-time itself, gravitational waves that echo the violence of the union. But why do these cosmic meals create different outcomes? Why does one merger produce a grand, structured spiral like the Milky Way, while another results in a smooth, football-shaped elliptical galaxy? The answer lies in the cannibal's diet. Spiral galaxies like ours are delicate structures, thin disks of stars and gas that require a relatively quiet history to maintain their shape. They typically grow by consuming small, gas-rich dwarf galaxies. These snacks add new material to the disk, fueling ongoing star formation without completely disrupting the spiral's elegant rotation. It is a gentle form of cannibalism that builds upon an existing structure, A major merger, however, is a catastrophic event. When two large, gas-rich spiral galaxies of similar size collide, it is a chaotic blender. Their neat rotating disk structures are utterly destroyed in the gravitational turmoil. The ordered orbits of billions of stars are randomized. The immense gas clouds slam together, triggering a frenzy of star formation that rapidly uses up the galactic fuel. What emerges from this violence after billions of years is an elliptical galaxy. It has no disk, no spiral arms. Its stars move in random, swarming orbits like a hive of bees, creating that smooth, rounded shape. The merger has completely erased the original architectures of both galaxies, forging something entirely new from the wreckage. So the final form of a galaxy is a direct record of its most violent meals, a fossil of ancient cosmic consumption, written in the motions of its stars. That final form, the elliptical galaxy, is the universe's ultimate trophy of conquest. Unlike the delicate pinwheels of spiral galaxies, ellipticals are smooth, featureless, and often shaped like colossal, three-dimensional footballs. They contain little to no star-forming gas, and their billions of stars swarm in chaotic, random orbits, creating a dense, glowing cloud of ancient suns. These are not galaxies born this way, they are galaxies forged through relentless violence. The largest of them, the true behemoths, are almost always found sitting at the very heart of massive galaxy clusters, like monstrous spiders at the center of a cosmic web. Their position is no accident, it is the direct result of a brutal history. In the crowded environment of a galaxy cluster, gravitational interactions are constant. Over billions of years, the largest galaxy in the cluster acts as a gravitational anchor. Through a process called galactic cannibalism on an industrial scale, it systematically consumes every smaller galaxy that dares to orbit too close. It devours spirals, it tears apart dwarfs, and it even merges with other large ellipticals, growing ever more massive and dominant. This process strips away all structure, randomizes all stellar orbits, and uses up or blows away all the pristine gas, leaving behind only this smooth, ancient giant. The perfect example of this cosmic monarch is Messier 87, or M87. It reigns at the center of the Virgo cluster, a gathering of thousands of galaxies. M87 is a supergiant elliptical, a sphere of stars so vast it contains several trillion solar masses, dwarfing our own Milky Way. Its sheer size is a testament to an unimaginable number of galactic mergers. But M87 offers us more than just silent proof of its past feasts. It actively shows us the energy those feasts released. From its core erupts a spectacular jet of superheated plasma, stretching for thousands of light years into space. This jet is powered by the galaxy's supermassive black hole, an object so famously massive its shadow was the first ever directly imaged. That black hole did not grow to its immense size in isolation. It was fed likely during those violent merger events when torrents of gas were funneled into the galactic center. The energy from that falling material now powers the brilliant jet, a beacon that screams of the galaxy's violent history. So when we look at M87, we are not just looking at a giant elliptical galaxy. We are looking at the final, quiet state of a cosmic battlefield, a predator that ate everything within its reach and now rests, its power still echoing from its core. But what weaves this web of gravity that orchestrates the entire feast? The true puppet master behind every act of cosmic cannibalism is something we cannot even see. Dark matter is the invisible architecture of the universe, the hidden skeleton upon which the luminous galaxies are draped. Without it, the grand, structured cosmos we observe simply could not exist. Think of a vast, empty spiderweb, glistening with dew in the morning light. The dewdrops are the visible galaxies, bright and beautiful, but the web itself, nearly invisible yet providing all the structure and strength, that is dark matter. It does not emit, absorb, or reflect light, making it completely undetectable to our telescopes. We only know it is there because of its immense gravitational pull on the things we can see, like stars and entire galaxies. This pull is why galaxies spin as fast as they do without flying apart, and it is the very reason they can capture and consume one another. A galaxy's dark matter halo is its true body, extending far beyond the last visible star. For a spiral like the Milky Way, the glittering disk of stars we see is perhaps 100,000 light years across, but its dark matter halo is a colossal sphere, stretching for millions of light years in every direction. When two galaxies approach each other, it is not their stars that first make contact. Long before the visible edges touch, these vast invisible halos of dark matter begin to intertwine and interact gravitationally. This is the point of no return. The dark matter web of the larger galaxy ensnares the smaller one, beginning the process of dynamical friction that will slowly drag the victim inward. The fate of the smaller galaxy is sealed not by the stars, but by this invisible embrace. To understand the patterns of galactic cannibalism we see in the sky, scientists must first simulate this dark cosmic dance. They use some of the world's most powerful supercomputers to model how these immense halos of dark matter form, evolve, and interact over billions of years. These simulations show us how the universe's large-scale structure, the great filaments and voids, emerge from the gravitational pull of dark matter. Galaxies form at the densest knots in this cosmic web, and they are funneled along these dark matter highways toward each other, destined for eventual mergers. When astronomers compare these dark matter-only simulations with the actual observed distribution of galaxies and stellar streams, the match is startling. It confirms that the ghostly hand of dark matter is guiding every collision, every tidal tear, every act of creation through destruction. So the next time you look at a serene image of a spiral galaxy, remember that its beautiful shape is just the visible decoration on a form shaped by an immense, unseen presence, a presence that is constantly writing the story of cosmic cannibalism in the silent language of gravity. These ghostly rivers of stars are the final, fading evidence of a galaxy's last meal. We call them stellar streams, and they are the forensic proof of cosmic cannibalism, the galactic equivalent of finding a few scattered bones and reconstructing the entire animal. Imagine a galaxy not as a solid spinning plate, but as a vast collection of stars held together by their mutual gravity. When a larger galaxy's tidal forces grab hold, it does not destroy that gravity all at once. Instead, it stretches the victim like cosmic taffy, pulling its stars into a long, looping river that continues to orbit the cannibal galaxy for billions of years. This river, glowing with the faint light of millions of suns, is a stellar stream. It is the leftover ribbon of a galaxy that no longer exists as a coherent island, a skeleton orbiting its predator. Our own Milky Way is draped with these celestial scars. One of the most stunning is the Monoceros ring. It is a vast, loop-like structure of stars that wraps around the outer disk of our galaxy, far beyond the familiar spiral arms. For a long time, astronomers debated its origin. Was it a warped part of the Milky Way itself, thrown out of shape by some ancient disturbance? The motion and chemistry of its stars, painstakingly measured, told a different story. These stars are moving together on a distinct path, and they possess a chemical fingerprint distinct from the native stars of the Milky Way's disk. They are immigrants, the remains of a dwarf galaxy that was consumed perhaps billions of years ago, its body now stretched into this magnificent, haunting ring. The evidence becomes even more dramatic when we look beyond our galactic home. Take the spiral galaxy known as NGC 5907. In visible light, it appears as a beautiful edge on pinwheel. But when astronomers used very long exposures to capture its faint outer light, they revealed something astonishing. Surrounding the galaxy is a gigantic, complex loop of stellar debris, a stream so immense it makes the galaxy at its center look like a jewel caught in a web of ghostly silk. This stream is the shredded corpse of a dwarf galaxy that was torn apart in multiple passes, its stars flung into these majestic, concentric rings. It is a snapshot of a cannibal act frozen in time, a display of gravitational artistry on a scale that defies human comprehension. So how do astronomers read this crime scene? They become stellar detectives. By using powerful telescopes and instruments like the Gaia spacecraft, they do not just map where these stream stars are, they track how they are moving. The precise velocity and direction of each star in the stream tell the story of the original dwarf galaxy's orbit and how it was torn apart. Even more telling is stellar archaeology, the study of a star's chemical composition. Stars born together in the same galactic nursery forge their unique elemental signatures from the gas clouds around them. By analyzing the light from stars in a stream, astronomers can read this chemical DNA. If all the stars in a stream share a similar, distinct mix of elements, like low amounts of heavy metals, It confirms they all came from the same small, primitive galaxy. This allows scientists to not only identify the victim, but to estimate when the merger happened. Younger, tighter streams point to a more recent feast, while older, more diffuse ones speak of ancient violence. From a few faint rivers of light, we can reconstruct the mass, the age, and even the life story of a galaxy that vanished eons ago, its entire history written in the scattered motions of its orphan stars. But the cosmic food chain leaves behind more than just glittering streams. Some of its most enigmatic survivors are nearly invisible. Scattered throughout the universe are objects that defy our expectations of what a galaxy should be. They're called ultra-diffuse galaxies, and they are cosmic ghosts. Imagine a galaxy as large as the Milky Way, spanning tens of thousands of light years, but containing only 1% of its stars. These are not dense, brilliant cities of stars, but vast, faint clouds where suns are so widely scattered that you could fly a spaceship through one and hardly notice. For a long time, these faint smudges on telescope images were overlooked or dismissed as camera artifacts, but with modern, ultra-sensitive telescopes, we have begun to find them in large numbers, and they pose a profound mystery. Are they failed galaxies that never managed to form mini-stars, born in a void with too little gas, or are they something far more haunting, the stripped-down survivors of a cannibal's attack? This question cuts to the heart of galactic evolution. One compelling theory suggests that some ultra-diffuse galaxies are not failures at all, but the resilient cores of galaxies that had a very close encounter with a predator. Picture a small, normal dwarf galaxy orbiting a giant. As it makes its first perilous pass, the cannibal's tidal forces do not completely destroy it. Instead, they act like a cosmic thresher, violently stripping away the galaxy's outer layers of gas and stars. What remains is the dense central core, now robbed of its material to make new stars and stretched into a large, faint, diffuse shape. It is a galaxy that has been skinned alive, its bright flesh torn away, leaving behind a ghostly skeleton that continues to orbit its attacker. The most famous example of this mystery is a galaxy known as Dragonfly 44, lurking in the distant Coma cluster. When astronomers first measured it, they were stunned. Dragonfly 44 has the width of the Milky Way, but emits only a faint whisper of starlight. Yet when they studied the motions of its few visible stars, they found them whizzing around at incredible speeds. The only way such a faint galaxy could hold onto stars moving that fast is if it was anchored by an immense amount of mass, a colossal halo of dark matter. In fact, calculations suggest Dragonfly 44 is 99.99% dark matter. It is essentially an invisible gravitational framework with a sprinkling of stars, like a few specks of dust caught in an unseen web. This discovery paints a startling picture. Dragonfly 44 may be the pristine skeleton of a galaxy, the dark matter halo that once held a thriving dwarf galaxy together. The cannibal did not consume the dark matter. It cannot be torn apart by tides in the same way. It simply stripped away all the luminous flesh, the gas and stars, leaving this massive, dark ghost behind. If this is true, then ultra-diffuse galaxies like Dragonfly 44 are not oddities. They are the silent, enduring witnesses to cosmic violence, the dark matter graves of galaxies that were eaten. They remind us that what we see with our telescopes is only the luminous tip of a much deeper, darker reality, a reality shaped by an endless cycle of creation and consumption. The ghostly remains of ultra-diffuse galaxies are not the only legacy of these violent mergers. The cannibal's feast can also ignite the most brilliant beacons in the cosmos. At the very heart of this process lies a supermassive black hole, a cosmic furnace that awakens during the chaos of a galactic meal. When two galaxies collide, it is not just their stars that mingle. Immense reservoirs of cold gas and dust, the raw fuel for star formation, are violently stirred. In the gravitational turmoil, these gas clouds lose their orderly motion and begin to tumble inward, funneled by the millions toward the very center of the merging system. There they encounter the waiting black holes. As the gas spirals down into the gravitational well, it compresses and heats to millions of degrees, glowing with an intense, hellish light before vanishing past the event horizon. This infalling material does not go quietly. The process creates an accretion disk, a whirling, superheated maelstrom of matter around the black hole. The friction and magnetic forces within this disk are so extreme that they can blast out colossal beams of energy and matter, transforming the galactic core into what astronomers call an active galactic nucleus, or a GN. Think of the black hole as the cannibal's ultimate digestive system. It takes the shredded material of the consumed galaxy and converts it into pure, radiant energy. The most extreme form of this is a quasar, an GN so phenomenally bright it can outshine its entire host galaxy. A single quasar can blaze with the light of 1 trillion suns, visible across billions of light years. For a time, this brilliant beacon becomes the dominant feature of the merged galaxy, a screaming announcement of the violent feast taking place. We see this connection clearly in the modern universe. Many of the brightest quasars and most active galaxies are found in systems that show clear signs of recent or ongoing mergers. Their distorted shapes, tidal tails, and chaotic structures are the visible hallmarks of cannibalism, while the brilliant core is the signature of the black hole's feeding frenzy. This energy output is not just a spectacular light show, it is a fundamental regulatory force. The intense radiation and powerful jets pouring from the active black hole can blow away the remaining gas in the galaxy, shutting down star formation for good. It is the cosmic equivalent of a blast furnace that sterilizes its own kitchen. This process helps explain why giant elliptical galaxies, the products of major mergers, are often filled with old, red stars and possess little gas to make new ones. The black hole's feast ultimately ends the galaxy's ability to create, leaving behind a quiet, aging giant. So the next time you see an image of a brilliant quasar, remember you are not just looking at a distant point of light. You are witnessing the final, radiant course of a cosmic cannibal's meal, a black hole shining with the stolen substance of an entire galaxy. This brilliant beacon of a feeding black hole is a story that will play out in our own cosmic backyard, with a character we have yet to properly introduce. Our local group of galaxies is not just a stage for the coming collision between the Milky Way and Andromeda. There is a third major player in this drama, a beautiful spiral known as the Triangulum Galaxy. Seen through a small telescope, it is a delicate face-on pinwheel of stars and glowing gas, the third largest galaxy in our local neighborhood. For a long time, its role seemed simple, a distant satellite orbiting the mighty Andromeda. But recent observations have rewritten its story, revealing a far more dynamic and perilous future. Precise measurements of its motion show it is not just idly circling Andromeda, it is on a vast, elliptical orbit that brings it incredibly close. In fact, some data suggest the Triangulum Galaxy may have already made a close pass by Andromeda several billion years ago, a glancing blow that stirred its gas and shaped its stars. This transforms it from a mere companion into a potential victim, caught in a slow-motion dance of capture and consumption. Scientists have run the gravitational equations forward in time, creating simulations of this cosmic trio's fate. The results are both beautiful and terrifying. They show that long before the Milky Way and Andromeda make their final merger, the Triangulum Galaxy's fate will likely be sealed. On its next close approach, the difference in size and power is simply too great. Andromeda's immense gravitational grasp will pull Triangulum apart. The smaller spiral will be stretched and distorted, its beautiful structure shredded into great luminous rivers of stars that will wrap around Andromeda, adding to its already massive stellar halo. Its gas will be compressed, triggering a final, furious burst of star formation before being siphoned away or blown out by the energy of the merger. In these simulations, the Triangulum Galaxy does not vanish in a flash. It dissolves over hundreds of millions of years, its essence becoming one more layer in the history of its cannibal neighbor. This possibility adds a profound layer of intrigue to our local cosmic story. If Triangulum is indeed on a long-term orbit and destined for consumption, then we are not just watching two giants prepare for a clash. We are witnessing a prelude, an appetizer before the main course. Andromeda, the voracious predator we have already met, may be about to demonstrate its power on a galactic scale right before our eyes, on a timescale astronomers can almost comprehend. Furthermore, the idea that this might be Triangulum's second pass makes it a cosmic survivor, a galaxy that once brushed with destruction and escaped, only to be drawn back in by the inescapable pull of gravity. Its current undisturbed spiral shape suggests it survived that first encounter relatively intact, a testament to the delicate balance between destruction and preservation. But the clock is ticking. Its serene beauty today masks a future of certain violence, a reminder that in the cosmic food chain, no beautiful spiral is ever truly safe. The fate of the Triangulum galaxy is a specific, ongoing script being written in the language of gravity, a preview of the cannibal's methods that will one day be used on our own Milky Way. The ultimate expression of this cosmic hunger is not found in lonely galaxies, but in the most crowded neighborhoods of the universe. To understand true cannibalism on a grand scale, we must zoom out far beyond the fate of a single spiral to witness the dynamics of an entire galaxy cluster. These are the metropolises of the cosmos, vast gatherings of hundreds or even thousands of galaxies, all bound together in a single, immense web of gravity. And in the heart of every great cluster, there is almost always a king. Astronomers call it the brightest cluster galaxy, a title that barely hints at its violent origin story. This is not merely the largest galaxy in the neighborhood, it is a monster forged through relentless, systematic consumption on an industrial scale. The process here is more brutal than a one-on-one merger. In the dense core of a cluster, galaxies swarm like bees in a hive, constantly buzzing past one another at tremendous speeds. When a smaller galaxy flies too close to the central giant, it doesn't just get slowly torn apart by tides. It experiences what scientists term galactic harassment. Each close gravitational encounter, each high-speed pass acts like a cosmic slap. Over millions of years, these repeated slaps strip away the smaller galaxy's outer stars and gas, weakening its structure and stealing its momentum. This harassment paves the way for the final act, cannibalism. The weakened victim, its orbit decayed by this constant gravitational friction, is finally captured. It is drawn into the immense body of the brightest cluster galaxy and utterly assimilated. The central galaxy grows not by eating one or two neighbors, but by consuming hundreds over the lifetime of the cluster. The perfect example of this lies some 320 million light-years away, in the constellation Coma Berenices. The Coma cluster is a sprawling city of over 1,000 galaxies. And at its very heart, there is not one but two supergiant elliptical galaxies, named NGC 4874 and NGC 4889. They are monstrous. Each is nearly 20 times the mass of our Milky Way, vast spheres of ancient stars that glow with the combined light of 1 trillion suns. These are not just brightest cluster galaxies, they are the archetypal cannibals. Studies of their faint outer light reveal a shocking truth. The smooth, serene halos that surround these giants are not smooth at all upon close inspection. They are a chaotic graveyard, a patchwork of countless shredded galaxies. The stars in these halos move in every direction with no common rotation because they did not form here together. They were thrown here from hundreds of different galactic systems that were torn apart and absorbed. By analyzing the motions and chemistry of these halo stars, astronomers have estimated that each of these central behemoths has consumed perhaps hundreds of smaller galaxies to achieve its staggering size. They sit at the gravitational bottom of the cluster, the ultimate sink where everything eventually falls. Their serene, featureless appearance is the final quiet after an eon of storms, the uniform smoothness that results from blending together the distinct architectures of countless victims. To live in such a galaxy would be to orbit in a sky of profound silence, a sky built from the ruins of an entire cosmic community. That serene, featureless giant at the heart of a cluster is the end of a long evolutionary road. To understand how a galaxy gets there, we need a map of the possible destinations. For nearly a century, astronomers have used a simple but powerful classification system called the Hubble sequence. Picture a tuning fork. On one prong, you have spiral galaxies like our Milky Way with their elegant rotating disks and central bulges. They are categorized by how tightly wound their arms are and the size of their central bulge. On the other prong, you have elliptical galaxies, ranging from nearly spherical to more oval shapes, all smooth and without structure. Connecting the two is a bar, representing barred spiral galaxies, which have a central bar of stars. Off to the side are irregular galaxies, the misfits with no defined shape. This sequence was once thought to be an evolutionary path, with galaxies starting as ellipticals and somehow spinning out into spirals. We now know that idea is backwards. The true engine driving a galaxy from one branch of the tuning fork to the other is violence, specifically the cosmic cannibalism we have been exploring. A spiral galaxy is a delicate rotating system. Its beautiful disk requires a relatively quiet life to maintain its structure. It can snack on small, gas-rich dwarfs, which adds fuel for new stars and gently builds up its mass without major disruption. This is galactic nurture through gentle meals, but a major merger, a head-on collision with another spiral of similar size, is a catastrophic event. It is the ultimate act of nurture through violence. The gravitational chaos of such a collision completely randomizes the orderly, circular orbits of billions of stars. The neat disk is shattered, the immense gas clouds slam together, triggering a brief, furious firestorm of star formation that rapidly uses up all the available fuel. What emerges from this billion-year-long turmoil is no longer a spiral. The stars settle into a new configuration, swarming in random directions like a hive of bees, creating that smooth, rounded shape. The galaxy has been fundamentally transformed, moving from the spiral prong of the Hubble tuning fork to the elliptical branch. This process solves a long-standing mystery. For decades, astronomers debated the nature versus nurture of galaxies. How much of a galaxy's final form is dictated by the initial conditions of its birth, the density of its primordial gas cloud, its spin, and how much is sculpted by its later interactions and mergers. We now see that both are crucial, but for the largest galaxies, nurture in the form of cannibalistic mergers is the dominant force. A galaxy might be born a spiral, but its fate is not sealed. Its place on the Hubble sequence is a living record, a snapshot of its most violent life experiences. An isolated spiral in a quiet part of the universe may retain its pinwheel shape for eons, a product of its initial nature. But place that same spiral in a crowded cluster, and the nurture of relentless harassment and eventual consumption will rewrite its story, transforming it into an elliptical giant. The smooth, red, and dead ellipticals we see are not born that way. They are made through a history of colossal consumption. Their very shape is the signature of a cannibal's past, a fossil of ancient violence written in the random swarm of a trillion stars. The serene giants we see today were forged in a far more violent, crowded past. To find the first cosmic cannibals, we must peer back to the dawn of time itself, and we now have the ultimate time machine to do it. The James Webb Space Telescope, with its unprecedented infrared vision, is looking back over 13 billion years, capturing light from the universe's first generations of galaxies. What it has found is not what anyone fully expected. Instead of seeing only tiny infant galaxies slowly coalescing, Webb has spotted monstrously large, fully formed galaxies shining in the cosmic darkness when the universe was less than 500 million years old, a mere infant by cosmic standards. These are not the delicate building blocks we predicted. They are cosmic titans in a nursery. Their existence is a profound puzzle. How could something so massive assemble so quickly? The old models of galaxy growth, of slow, steady accretion of gas over billions of years, simply cannot explain it. The universe did not have enough time for such giants to grow by normal means. This forces astronomers toward a startling conclusion. The cosmic food chain, the process of galactic cannibalism, must have begun almost immediately after the first stars flickered to life. In that primordial era, the universe was a much denser, more chaotic place. Galaxies were packed closer together, buzzing in a hot, dense soup of gas. In such an environment, mergers would have been frequent and ferocious. Instead of the slow, graceful dances we see today, the first galaxies likely engaged in a period of hyper-cannibalism, a rapid-fire series of collisions and consumptions that allowed them to balloon in size at a breakneck pace. Imagine the early cosmos not as a quiet, expanding void dotted with lonely lights, but as a raging, churning sea where galactic islands were constantly crashing together, merging and growing in a frantic race to become the first giants. The James Webb data is showing us the winners of that race, galaxies that gorged themselves on their neighbors in the universe's first frantic chapters. This rewrites our timeline completely. The cosmic cannibal is not a late-stage predator that emerges after eons of quiet growth. It appears to be one of the universe's original architects, a fundamental mechanism for building structure from the very beginning. The food chain did not start slowly. It began with a violent, all-consuming feast. These ancient giants glimpsed by James Webb force us to ask a difficult question. How can we possibly test a theory of the cosmos that spans billions of years? We cannot run a controlled experiment on two galaxies, and we certainly cannot wait around to watch them collide. The answer lies not in a telescope, but in a computer. To unravel the cosmic food chain, scientists build entire universes inside machines. Projects with names like Illustris TNG and EAGLE are not video games. They are some of the most sophisticated scientific simulations ever created. Running on the world's most powerful supercomputers for months at a time, they begin with the basic ingredients of the early universe, a nearly uniform soup of dark matter and hydrogen gas, governed by the known laws of physics. Gravity is switched on and the simulation begins. From this simple starting point, a virtual cosmos unfolds. Dark matter clumps into a vast cosmic web. Gas flows along these filaments, cools and collapses into the first stars and galaxies, and then the cannibalism begins. As these virtual galaxies evolve, they move within the dark matter scaffold, drawn together by gravity. They merge, they tear each other apart, they grow. The simulations track everything: the birth and death of stars, the explosive feedback from supernova, the growth of supermassive black holes and their energetic jets. It is a breathtaking dance of creation and destruction, all calculated one mathematical step at a time. The true power of these tools is revealed when we compare their output to our real night sky. Scientists can take a snapshot from the simulation, a moment frozen in cosmic time, and generate a synthetic telescope image. They can apply the same filters and resolution limits as our real observatories. The results are often uncanny. Side-by-side comparisons show virtual galaxies with the same majestic spiral arms, the same distorted shapes from recent collisions, and the same faint, ghostly stellar streams wrapping around their hosts as we see in reality. The simulations do not just reproduce pretty pictures, they reproduce the statistical patterns of the universe. They predict, for instance, how many dwarf galaxies should orbit a galaxy like the Milky Way and what their orbits should look like. When astronomers then point telescopes at our own galactic halo, they find the real dwarf galaxies moving in precisely those predicted orbits. It is a stunning validation that the physics coded into these virtual worlds is capturing the true story of cosmic evolution. These digital universes have become essential forecasting tools. By creating thousands of simulated Milky Ways, each with a slightly different history of mergers, scientists can run the clock forward. They can ask statistically, what is the most likely fate for a galaxy like ours in a neighborhood like ours? The simulations consistently show the same narrative: the gradual consumption of remaining satellite galaxies and the inevitable slow-motion dance and merger with Andromeda. They show us where to look for the faintest stellar streams, the ones our current telescopes might have missed, guiding the next generation of observations. In a very real sense, these simulations are time machines, allowing us to witness the birth, life, and cannibalistic death of galaxies on a timescale we can comprehend. They transform the cosmos from a collection of beautiful but static snapshots into a dynamic, evolving movie, where every galaxy's shape is a chapter in a story written by gravity, a story we are now learning to read by writing it ourselves. These digital time machines have given us the script, but the proof is written in the stars themselves. A new scientific field has emerged to read that story, a kind of cosmic detective work called galactic archaeology. It is built on a simple, powerful idea. A galaxy is not born in a single moment. It is a living history book, and every star within it is a page carrying clues about where and when it formed. By studying the motions, positions, and chemical makeup of millions of individual stars, archaeologists can excavate our galaxy's past, layer by layer, uncovering the ancient mergers that built our home. Think of it like this: if you walk into a bustling city square and listen, you will hear many different accents and languages. Each tells you something about where that person or their ancestors came from. Galactic archaeology does the same for the Milky Way. It listens to the stars. The revolutionary tool making this possible is the Gaia spacecraft. Gaia is not taking beautiful pictures of nebulae. Its mission is staggeringly precise measurement. It is constructing the largest and most accurate three-dimensional map of our galaxy by repeatedly scanning the sky, pinpointing the position, distance, and most importantly, the motion of over 1 billion stars. This gives us a dynamic movie of the Milky Way, not just a static snapshot. We can see how stars are moving right now, and by applying the laws of physics, We can rewind their orbits to see where they came from billions of years ago. This kinematic data is one piece of the puzzle. The other is stellar chemistry, gathered by powerful ground-based telescopes. When a star forms, it condenses from a cloud of gas, locking in the chemical fingerprint of that cloud. Stars born together in the same dwarf galaxy will share a distinct chemical signature, like siblings sharing DNA. By analyzing the faint light from a star, astronomers can determine its precise recipe of elements, how much iron, magnesium, or europium it contains. Combine the chemical DNA with the kinematic history from Gaia, and you have an incredibly powerful forensic tool. This is how galactic archaeologists have begun to assemble the Milky Way's family tree. They have identified distinct populations of stars moving together through the galactic halo, all sharing the same unusual chemical fingerprint, like a group of strangers in that city square, all speaking the same rare dialect. These are the stars from consumed galaxies. The most famous of these stellar families is known as Gaia Enceladus, sometimes called the Sausage Galaxy. Billions of years ago, a dwarf galaxy roughly the size of the Large Magellanic Cloud collided with the young Milky Way in a massive, head-on merger. The violence of that event scrambled its stars into highly elongated, radial orbits like a cosmic sausage and scattered them throughout our halo. Today, thanks to Gaia and chemical surveys, we can pick out those stars. They move differently and have less metal content than the Milky Way's native stars, clearly marking them as immigrants from a catastrophic ancient feast. But Gaia Enceladus is just one chapter. Archaeologists have identified other distinct streams and clusters, each the remnant of a different meal. There is the Helmy stream, the Sequoia galaxy, and the remains of the poorly named but very real galaxy known as Pontus. Each of these groups tells a story of capture, disruption, and assimilation. Our galaxy's halo is not a random swarm of ancient stars. It is a carefully sorted archaeological dig with layers of debris from different merger events. This turns the entire Milky Way into a detailed crime scene. We are not just seeing that a crime occurred, we are identifying the individual victims, estimating their original mass, and determining the approximate time of the merger. We are reconstructing the biography of a cannibal from the bones of its meals, written in the silent language of starlight and motion. But the story of cosmic cannibalism has a second, far more spectacular act. While a galaxy can grow steadily by nibbling on dwarfs, its most transformative moments come from a head-on collision with an equal. This is a major merger, the universe's ultimate construction project, where two large spiral galaxies meet and are completely reborn. The process is not a quick smash, but a breathtakingly slow and violent ballet that unfolds over more than 1 billion years. It begins with a gravitational courtship. As two spirals drift close, their mutual gravity starts to warp their beautiful disks long before they touch. Spiral arms stretch and distort, and bridges of gas begin to form between them. Then comes the first fateful pass. The galaxies do not hit like solid billiard balls, but swoop through each other, their stars sailing past in the vast emptiness between them. Yet this near miss is catastrophic. Their immense gravitational fields pull on each other with irresistible force, unleashing chaos. The most visible sign of this violence is the creation of tidal tails. These are colossal rivers of stars and gas, flung out from the galaxies by gravitational slingshots, stretching for hundreds of thousands of light years into space. They are the galactic equivalent of two dancers spinning so fast that their hair streams out behind them. This phase is captured perfectly by a pair of galaxies known as the Mice, officially called NGC 4676. In telescope images, they look exactly like two rodents scurrying away from each other, connected by long, luminous tails of stolen material. Their distinct cores are still separate, but their bodies are already shredded, a snapshot of the merger's furious opening chapter. After this first pass, the galaxies, now wounded and intertwined, are bound forever. They swing apart on elongated orbits, only to be pulled back together by gravity's unbreakable tether. Over hundreds of millions of years, they make several more close passes, each one stripping away more structure, injecting more chaos. The neat spiral patterns are gone, replaced by a tangled mess of dust lanes, glowing gas, and frantic star formation. The classic example of this middle stage is the antennae galaxies, or NGC 4038 and 4039. Here, the two galaxies are so deeply entwined that their original shapes are almost unrecognizable. From their cores erupt two enormous curved tidal tails that resemble the delicate antennae of an insect, giving the pair its name. Within those tails and at the collision point between the galaxies, the compressed gas clouds ignite, lighting up with the pink glow of a million stellar nurseries. The galaxies are not just being destroyed, they are giving birth to new star clusters at a ferocious rate. Finally, after eons of this gravitational dance, the last act begins: coalescence. The two galactic cores, each harboring a supermassive black hole, sink toward the center of the combined mass. The random motions of billions of stars, stirred by the repeated passes, begin to average out. The long tidal tails, robbed of momentum, fall back in or drift away. What remains starts to settle into a new, smooth configuration. The ordered rotation of the spirals is gone, replaced by a swarm of stars moving in every direction. The gas is either used up in final bursts of star formation or blown away by the energy of the merging black holes. After more than 1 billion years, the violent ballet concludes. Where two magnificent spirals once spun, a single new galaxy emerges, smooth and featureless, an elliptical giant. This is the ultimate fate of a major merger, a complete metamorphosis where cannibalism does not just add mass, it erases the past and forges an entirely new future from the cosmic wreckage. Our galaxy's halo is a battlefield of ancient mergers, but not every small galaxy that wanders close is immediately devoured. Orbiting giants like the Milky Way and Andromeda are entire populations of dwarf satellite galaxies, tiny islands of stars held together by their own gravity. These cosmic companions present a puzzle. Some, like the Sagittarius dwarf, are clearly being torn apart, their stars streaming into the cannibal's halo. Others, however, appear stable and serene, seemingly untouched by the violent forces around them. What determines whether a dwarf galaxy survives or becomes a meal? The answer lies in a delicate balance of cosmic defenses. One key factor is a dense, resilient core of dark matter. Think of a dwarf galaxy as a peach. If it has a large, soft flesh of stars and gas with only a small dark matter pit at its center, it is vulnerable. Tidal forces can easily strip that flesh away. But if the galaxy is more like a plum with a very dense, compact dark matter seed making up most of its mass, that gravitational anchor can hold the system together against the cannibal's pull. Another factor is distance. A dwarf galaxy on a wide, lazy orbit far from the cannibal's dense inner regions experiences a much gentler gravitational tug, allowing it to circle for billions of years relatively unscathed. Speed is also a shield. A satellite galaxy on a fast slingshot trajectory might zip through the perilous inner halo too quickly for the tidal forces to get a firm, destructive grip. Our own Milky Way showcases this entire spectrum. The large and small Magellanic Clouds, the two most famous satellites visible from the southern hemisphere, are on stable, if dynamic, orbits. They are massive enough and moving with enough speed that they have survived for eons, though their gas is being stripped away to form the vast Magellanic Stream. In contrast, dozens of fainter, ultra-faint dwarf spheroidals dot the galactic halo, many so diffuse they seem to be on the brink of dissolution. This population of survivors, however, is smaller than we expected. For decades, cosmologists have grappled with the missing satellites problem. The most sophisticated supercomputer simulations of cosmic structure, which model how dark matter clumps in the early universe, predict that a galaxy like the Milky Way should be surrounded by many hundreds, even thousands, of small dark matter halos, the potential homes for dwarf galaxies. Yet we have only observed a few dozen. Where are all the missing satellites? Galactic cannibalism offers a compelling part of the solution. Many of those predicted small halos were likely never able to form many stars at all, remaining dark and invisible. But a significant number of others probably did form stars, only to be consumed by the central galaxy long ago. The faint stellar streams we now see, like Gaia and Enceladus, are the ghosts of those missing satellites. The cannibal did not just eat a few obvious victims. It systematically cleared its cosmic neighborhood over billions of years, absorbing countless smaller systems and leaving behind only the most resilient or distant survivors. This means the dwarf galaxies we see today are not a random sample. They are the exceptional few, the ones with the right combination of a tough dark matter core, a fortunate orbit, or sheer speed to endure in the shadow of a giant. There are the lucky remnants of a much larger ancient population, living proof that in the cosmic food chain, survival is the exception, not the rule. This violent dance of creation and destruction has a direct, measurable heartbeat, the rate at which new stars are born. A galactic merger does not just rearrange stars, it fundamentally resets this cosmic clock. In the chaotic core of two colliding spirals, something spectacular ignites, a phenomenon astronomers call a starburst. Picture the immense reservoirs of cold hydrogen gas that fuel star formation in each galaxy. In a normal, quiet spiral, this gas is spread thin and rotates peacefully, but during a merger, those gas clouds are violently slammed together. The collision creates immense shockwaves, compressing the gas into incredibly dense, turbulent knots. Under this sudden, extreme pressure, gravity wins faster than ever. These knots collapse not into single stars, but into whole clusters of them, thousands at a time. The galaxy becomes a frantic stellar nursery, burning through its entire galactic gas supply in a brief, brilliant frenzy. We see this in action in systems like the antennae galaxies, where the region between the two cores glows pink with the light of newborn stars, a firestorm of creation brighter than the rest of the galaxy combined. For a short cosmic moment, the cannibal's feast becomes a feast for star formation itself, a final glorious burst of youth triggered by the violence of the merger. But this firestorm cannot last. The same forces that ignited also ensure its end. The furious starburst is a runaway process that consumes the available fuel at a staggering rate. More critically, the merger awakens the sleeping giants at the galactic centers, the supermassive black holes. As gas funnels toward them, they erupt as active galactic nuclei, blazing with radiation and blasting out jets of energetic particles. This energy floods the remaining gas in the galaxy, heating it to such extreme temperatures that it can no longer cool and collapse to form new stars. In the most violent mergers, powerful shockwaves can even blow the gas entirely out of the galaxy, ejecting it into the vast intergalactic void. This is the cannibal's final, paradoxical act. It first triggers a spectacular birth of stars, and then systematically it sterilizes the galactic environment. After the merger is complete and the new elliptical galaxy has settled, the result is a system that is red and dead. Its population of stars ages together, glowing with the cooler, redder light of old suns. With no cold gas left to form new, hot blue stars, the galaxy's color shifts permanently to red. Its stellar birth rate plummets to zero. The cannibal's feast, therefore, writes the final chapter in a galaxy's life story. It dictates whether a galaxy will remain a vibrant, star-forming spiral for eons or be transformed into a quiet, aging elliptical, its future of creation extinguished by the very violence that once ignited it. This red and dead state might seem like the final chapter, but the cosmos has one more, even more extreme outcome to reveal. In the deepest reaches of space, astronomers have discovered the ultimate cosmic predators, systems so quiet and so dominated by a single entity that they have earned a haunting name: fossil groups. These are not active clusters buzzing with hundreds of bright galaxies. A fossil group is a galactic ghost town, a cluster environment where the process of cannibalism has run to its absolute conclusion. Imagine a metropolis where over eons, one colossal corporation systematically bought out and absorbed every other major business in the city. All that remains is the single towering headquarters, surrounded by a few small, independent shops too insignificant to notice. In cosmic terms, the headquarters is a supergiant elliptical galaxy, often one of the most massive galaxies known in the entire universe, and the small shops are a population of tiny, faint dwarf galaxies. Every other galaxy of substantial size, every potential rival, has been consumed by the central behemoth. This is the end stage of cannibalism in a dense environment, a snapshot of a cosmic food chain that has reached its final link. Finding these elusive fossils, however, is a tremendous challenge. By their very nature, they appear quiet and empty in visible light telescopes. You might see one brilliant giant and a handful of faint smudges, which could easily be mistaken for a lone galaxy with a few distant, unrelated companions in the foreground or background. To confirm a fossil group, astronomers need to prove that this giant galaxy sits at the heart of a massive gravitational, well worthy of an entire cluster. They need to find the ghost of the feast itself, The key evidence does not come from starlight, but from heat. When galaxies swarm together in a cluster, the space between them is not empty. It is filled with an incredibly thin yet searingly hot plasma that can reach temperatures of tens of millions of degrees. This intergalactic gas is heated to such extremes by the gravitational energy of the cluster itself, as galaxies and dark matter tumble within its immense pull. This gas glows not in visible light, but in high-energy X-rays. So to hunt for fossil groups, scientists turn to space-based X-ray telescopes like Chandra or XMM Newton. They point them at a candidate, a lone, giant elliptical, and look for a vast, symmetrical halo of X-ray emission surrounding it. Finding such a halo is the smoking gun. It proves that this single galaxy is sitting in the deep gravitational pit of what was once a full cluster of galaxies. The scale and temperature of the hot gas halo reveal the total mass of the original system, telling astronomers just how massive the feast truly was. The serene optical image is a lie. The X-ray vision reveals the colossal, energetic aftermath of a banquet where one galaxy ate everything else on the table. One of the most studied fossil groups lies about 290 million light-years away, centered on a galaxy named ESO 3060170. In optical images, it is a classic smooth elliptical, albeit a very large one, but in X-rays its true nature is unveiled. It is enveloped by a gigantic spherical cloud of million-degree gas that extends for over 1 million light-years. The energy required to heat and hold such a vast atmosphere of gas is enormous, equivalent to the gravitational binding energy of an entire cluster of galaxies. The sheer presence of this hot halo confirms that this galaxy is not alone. It is the surviving core of a once thriving community that it has entirely consumed. The dwarf galaxies that remain are mere spectators, orbiting a monarch that has eliminated all competition. Studying fossil groups like this one allows astronomers to test their models of cosmic evolution in extreme conditions. They represent a quiet, finished experiment in galactic cannibalism, showing us the ultimate fate of a cluster when given enough time and the right predatory giant. They are the cosmic equivalent of a single massive tombstone, marking the final resting place of dozens of galaxies that once were. This final, quiet state of a fossil group is not the end of the story, but a new beginning for the universe itself. The violence of galactic cannibalism is also a profound act of cosmic recycling. When two galaxies collide and merge, the chaos does more than just rearrange stars. It fundamentally changes the chemical makeup of the cosmos. In the furious starbursts and supernova explosions triggered by the merger, something vital is forged and flung into the void. Inside the hearts of stars, nuclear fusion cooks simple hydrogen and helium into heavier elements: carbon, oxygen, iron, all the way up to gold and uranium. When those stars die, either in gentle planetary nebula or in cataclysmic supernova, they spew these newly forged elements out into space. In a galactic merger, this process is supercharged. The enriched gas now laced with these heavy elements is not just stirred within the cannibal galaxy. The immense energies involved, from the shockwaves of colliding gas clouds to the powerful jets from awakened black holes, can blast this material clean out of the galaxy altogether. It is ejected at tremendous speeds, polluting the vast empty tracts of intergalactic space with the seeds of complexity. Think of it not as destruction, but as sowing. This intergalactic pollution, this scattering of stardust across millions of light years, is the universe's way of enriching its future. When gravity later pulls together a new cloud of pristine hydrogen and helium to form a next-generation galaxy, that cloud is no longer pure. It is already seeded with the heavy elements from ancient cannibalized systems. These elements are the building blocks of everything that is not a star: rocky planets, oceans, atmospheres, and ultimately, the chemistry of life itself. Our own existence is a direct product of this ancient violence. Every atom of carbon in your cells, every particle of iron in your blood, was forged in the heart of a star that lived and died long before our sun was born. But that star did not exist in isolation. It was part of a galactic system that likely underwent its own violent mergers, events that churned and enriched the galactic gas cloud from which our solar system eventually condensed. The specific mix of elements we find on Earth, in our asteroids, and in our sun's composition is a chemical fingerprint. It tells us that the nebula that gave birth to our solar system was not primordial. It was the recycled product of many generations of stars, whose lives and explosive deaths were likely accelerated and amplified by the cannibalistic mergers of our galaxy's ancestors. So when you look up at the night sky, you are not just seeing the aftermath of cosmic feasts, you are looking at the source of your own atoms, the gold in a wedding ring, the calcium in your bones, the oxygen you breathe. All were created in stellar furnaces and then scattered across the galaxy by the very gravitational storms we have been exploring. Galactic cannibalism, for all its violence, is the universe's great recycling program. It takes the simple products of the Big Bang and over billions of years of collision and creation, refines them into the rich diversity of elements that make planets and life possible. We are not just observers of this ancient story, we are its living consequence. This grand cosmic recycling raises a deeper question, one that goes beyond physics and into the realm of philosophy. Is the universe by its very nature violent? We have traced a story of relentless consumption, of galaxies tearing each other apart over eons. It paints a picture of a cold, mechanical cosmos driven by an insatiable hunger. Yet to call it violent in the way we understand the word is to misunderstand it entirely. There is no malice in gravity. There is no intent in a tidal force. This is simply the universe operating according to its foundational rules, a natural consequence of mass and attraction playing out across timescales we can hardly fathom. The cannibal galaxy feels no triumph, the consumed galaxy knows no fear. It is physics pure and unfeeling, so if it is not violence, what is it? Perhaps it is better understood as a cycle, the universe's most fundamental rhythm of change. We see this same pattern mirrored here on Earth in every healthy ecosystem. In a forest, a fallen tree is not a tragedy, it is a banquet. As it decomposes, it returns nutrients to the soil, fueling the growth of new saplings. The death of one organism becomes the life for countless others. Predation keeps populations in balance, ensuring the health and diversity of the whole. This is not cruelty, it is the engine of renewal. The cosmic food chain operates on the same principle, just at an unimaginable scale. The destruction of a dwarf galaxy is not an end. It is the dispersal of its enriched stars and gas, the seeding of future generations of solar systems within the cannibal. The colossal merger that ends two majestic spirals gives birth to a brilliant starburst and eventually a new type of galaxy altogether. Destruction and creation are two sides of the same coin, forever linked in a dance that builds complexity over time. This leads us to the most profound question of all: does this grand cycle have a purpose? Science cannot answer that. It can only describe the mechanisms, but in describing them, it reveals a universe that is dynamic, evolving, and strangely creative in its methods. The same force that tears galaxies apart also gathers the gas to form stars and the dust to form planets. From the ruins of ancient collisions come the very elements that make our world, and us, possible. So while we may see a predator in the cosmos, we might also learn to see a sculptor, one that uses gravity as its chisel and time as its canvas, endlessly reshaping the universe into new forms. This perspective doesn't diminish the scale of the events, but it reframes them. It asks us to hold two truths at once. The universe can be both breathtakingly fierce and astonishingly fruitful, all governed by the same silent, mathematical laws. This grand sculpting cycle of the cosmos is about to be captured in unprecedented detail. Our understanding of galactic cannibalism is poised for a revolution, not from rethinking old data, but from a flood of breathtaking new observations. A new generation of telescopes designed to see the faint and the wide is coming online, and they will turn the entire sky into a forensic lab for cosmic crime scenes. Leading this charge is the Vera C. Rubin Observatory, currently under construction in Chile. Its mission is simple yet monumental: to conduct a 10-year legacy survey of space and time, or LSST. Every few nights, its enormous mirror and giant camera will capture the entire visible southern sky in exquisite detail. It will not just take pretty pictures, it will make a movie of the universe, detecting changes and motions over time. For our story, this means something extraordinary. The Rubin Observatory will be a stellar stream hunter without equal. Its deep, repeated scans will reveal thousands of these faint, ghostly rivers around distant galaxies, mapping the debris of cannibalistic acts we never knew occurred. It will find streams so tenuous and ancient they are currently invisible, allowing us to trace the complete merger history of galaxies, including our own, with a clarity we can only dream of today. Joining this effort in space will be the Nancy Grace Roman Space Telescope, NAS, a next great observatory, while Hubble peered deeply at tiny patches of sky and Webb looks deeply into the infrared past. Roman will combine depth with an astonishingly wide field of view. Imagine being able to see the detail of a Hubble ultra-deep field, but covering an area of sky over 100 times larger. This power is perfect for taking a cosmic census. Roman will find and characterize millions of the faintest galaxies, including those elusive ultra-diffuse ghosts and the shredded remnants of dwarfs, across vast stretches of the universe. It will allow us to move from studying individual cases of cannibalism to understanding its statistics. How common is it for a galaxy like the Milky Way to have consumed a dozen satellites versus 50? How does the rate of mergers change across cosmic time? Roman's wide, sharp eyes will give us the data to answer these questions, transforming galactic archaeology from a meticulous study of a few nearby examples into a full-blown demographic science. Together, these instruments will provide an unprecedented three-dimensional map of cannibalism's aftermath. They will not just find streams, they will measure the motions of stars within them with incredible precision, letting us rewind the clock on thousands of galactic mergers simultaneously. They will peer into the halos of galaxies millions of light years away, dissecting their stellar populations to read their violent histories as clearly as we are now beginning to do with our own Milky Way. This incoming wave of data promises to rewrite the history of our cosmic neighborhood. It will likely reveal ancient mergers our galaxy underwent that left no obvious trace until now, and it may even discover previously unknown, massive satellites currently hiding in the galactic shadows, destined for a future meal. We're on the verge of shifting from knowing the plot of the cosmic cannibal story to reading every single page in every single galaxy across the universe. The silent, slow-motion feast that has shaped everything we see is about to be illuminated, and the menu is far more extensive than we ever imagined. We are surrounded by the evidence of these ancient feasts, but could we ever watch one happen in real time? The timescales of the cosmos work against us. You will never look through a telescope and see a galaxy vanish before your eyes, any more than you could watch a mountain range rise. A single galactic merger unfolds over hundreds of millions, even billions of years. Our entire species will come and go in a cosmic blink, yet in a profound way we are witnessing cannibalistic events right now. We are simply seeing different chapters of the same story spread across the universe. We see the opening act in close galactic pairs, their shapes already warped by mutual gravity, like two dancers beginning their first spin. We see the violent middle chapters in systems like the antennae galaxies, where two spirals are tangled in a frenzy of creation and destruction. And we see the quiet final chapters in the smooth, red ellipticals and the faint stellar streams that drape their halos. Each of these is a single frame from a billion-year-long movie, and by observing thousands of such frames, we can reconstruct the entire film. This means the ultimate cosmic cannibalistic event, the one that will redefine our own night sky, is already written in the stars. In roughly 4 to 5 billion years, the Milky Way and Andromeda will begin their own slow-motion collision. It will be the grandest merger our local universe will ever see, a dance of two titans that will last for eons. While we cannot live to see it, we have already seen its script performed countless times elsewhere. Every distorted galaxy, every tidal tale, every brilliant starburst we observe in the deep field is a preview of our own galaxy's distant, transformative fate. By studying them, we are not just learning about the universe, we are reading our own future, written in the light of galaxies far, far away. This cosmic story is not a rare exception, it is the universal rule. From the faintest stellar stream around the Milky Way to the supergiant ellipticals ruling distant clusters, cannibalism is the primary sculptor of the galaxies we see. It builds giants from the ruins of dwarfs, transforms elegant spirals into smooth ellipticals, and dictates the life and death of stars. The evidence is woven into the fabric of our own galactic home, a chronicle of ancient meals written in the motions and chemistry of a billion suns. And this grand cycle of destruction and creation is deeply personal. Every atom in our bodies that is heavier than hydrogen or helium, the carbon, the oxygen, the iron, was forged in the heart of a star. That star lived and died in a galaxy whose own history was shaped by these violent mergers. The very elements that make our world and our lives possible were scattered across space by the shockwaves of galactic collisions. We are quite literally stardust recycled through cosmic violence, so when you look up at the night sky, remember this profound truth. In the grand cosmic story, we are not just observers of cannibals, we are the children of cannibals. What does that perspective make you see when you gaze at the stars? Let us know your thoughts in the comments below. If this journey through the cosmic food chain expands your view of the universe, be sure to like and subscribe for more explorations into the deepest mysteries of space.